Do, do, do. All right, so I decided to read you guys the scripture that's on the sticky note outside my door. You know, there's these folks who put sticky notes with verses all over campus, right? And there's like a sign outside interdisciplinary. Their project is to put, I forget, like 2,000 scriptures on different doors or something. So if you notice, there's sticky notes all over the place with verses. This is the one that's outside my door. This is Titus 3, chapter 3, verse 14, which is kind of an odd verse taken out of context. I'm going to read a couple verses before it. So it's at the end of Titus. It says, "When I send Artemas and Tychus to you, I make every effort to come to me at Nicopolis, for I have decided to spend the winter there. Diligently help Zenas the lawyer and Apollos on their way, so that nothing's lacking for them. Our people must learn to engage in good deeds to meet pressing needs, so that they will not be unfruitful." That's what's on my door. Our people must also learn to engage good deeds to meet pressing needs, so they will not be unfruitful. In other words, get a job, be productive, do stuff, help people. You know, it's good advice to live by, I think. All right, I will begin with a word of prayer. So, Heavenly Father, we thank you again for this day. I thank you for this class, and just ask you to be with us, help us to glorify you what we do, and just to learn more about continuity, and just to encourage the students if they're struggling. Lord, in your name I pray, Lord Jesus. Amen. So guys, you know, some of you did not do too well on this quiz, and that's okay. That's the reason I have quizzes in here in part, guys, is that, you know, quizzes are like 8% of your grade, right? 80 points out of 1,000. And, ow. Whoa, try to do that again. No, no, actually don't. Actually don't. I did that once in physics. Not that exactly, but I was illustrating like friction by pushing a chair back and forth. And like I ended up hitting the wall, and then, well, no, I wouldn't even hit the wall. It's just like pushing a chair back and forth, and all of a sudden, like the instructor and like the room next to me started whacking on the wall, like, stop it, you know, because it's making so much noise. So, I don't know. I'd like to think somewhere downstairs below us, there's somebody going, ah, you know. Anyway, I'm just glad there's not so many people walking on the roof anymore. There used to be a lot of people walking on the roof. And when they walk on the roof, it makes these projectors shake up and down because the gazebo thing is right up there, you know. Come on, work. I plugged it in. What do you want from me? All right, maybe it's to change the source. No, HDMI, that's it. Well, come on. You can do it. Yes, you can do it. Oh, well, apparently I closed the, anyway, you guys already top-hatted, I hope. If not, it's really not a problem. The attendance sheet will go around here. Here it is. What's today? I'll let you add the date. I guess if we want to be correct, it's the 30th. All right, so what I was getting back to saying is a lot of you made pretty low scores on this, and that's useful because what that means is you found out you don't know something, right? Or at least you don't know it under time pressure, which means you need to fix that, right? Because there will at some point in the quasi-near future be a test, right? And the test will have similar time pressure, and also you will also not be allowed to work with a friend and or look up stuff on Google, et cetera, right? So kind of the same kind of the same conditions as the quiz, right? So that's why I give quizzes in here. I don't give quizzes in all my classes, but for you guys, since you're still sort of getting used to taking courses in math at Liberty, I think it's helpful, especially in this course where we have time to have some quizzes. Now, but if you didn't get the score you'd like on the quiz, I wouldn't be too discouraged. Just take it as an opportunity to learn. You know, I do drop like the lowest of like every 3, it's in the course planner, I forget it exactly, but I drop about 30% of your quizzes anyway. So even so, there is still a chance for recovery, although that's kind of less relevant now that we're on quiz 3. So anyway, let's just talk through the solutions. So the problem 1, this is, I mean, what is this problem about really? The problem is really about, do you know what these functions are and what their graphs look like? That's the most simple way to calculate a lot of these, or with a calculator, of course. So sine is everywhere continuous. Talk more about what that means today. But that means we can just plug in pi into x over 2. We get pi over 2. Sine of pi over 2 is 1. Some of you put a half. I don't know where that comes from. Problem B, some of you got like an imaginary number here. That's because you're not minding the cube root, right? It's a cube root. The cube root of any real number exists. It's a real number, all right? This one happens to be the cube root of minus 27, which is minus 3. Part C is you try to plug in the number, you can't. You get division by 0, right? So when that happens, what do? You got different options. One option would be to graph the function. If you graphed it properly, you'd see that it's got a volcano at 1. It's going up to infinity from both sides. Now, if you don't know how to graph, you're not confident about that, or it just takes you an inordinate amount of time to graph at your current state of understanding, that's fine. An alternative approach, once you plug it in and get something over 0, right? Not 0 over 0. 0 over 0 means there's algebra to do, something to understand. But here, if you plug the number 1 in, you get 3 over 0, right? One thing you could do is simply look at plugging into your calculator like 1.1. Try plugging 1.1 into the expression. Try plugging 0.9 into the expression. Both of those should give you pretty big numbers. I think like 300-ish. All right? Now the way I understand it, I like this algebra approach, which is that as x goes to 1, that means x is basically equal to 1 plus or minus a little delta. So if I plug that in and I do algebra, I get 3 times 1 plus or minus delta over plus or minus delta squared. Now delta compared to 1 is nothing. So I can just drop the plus or minus delta upstairs, intuitively speaking, right? It's essentially equal to just 3 over delta squared, because plus or minus squares to 1. So I can see through that little bit of algebra in the parentheses that this expression is essentially 3 over delta squared. And once I see that, I'm like, oh, it's infinity. Because 1 over a tiny number squared is something huge and positive because of the square, all right? Anyway, next one, some of you just like lost the exponential in the limit. I'm not sure what happened there. You know, sometimes you lose track of what you're doing mid-thought. That's fine. That's nice. It's understandable. Like fine is maybe the wrong word. You'd like to not do that. But basically here what I'm using is I'm using the continuity of the exponential. So let me not, right? So continuity of the exponential means I can take the limit outside and bring it inside. Of course, the limit of the square root of x plus the log 2 is just, 0 plus log 2. But then that gives us e to the natural log of 2, which simplifies to 2. Now, a lot of you got that. That's great. This one here is a little bit trickier. Notice that this is the limit as x goes to 0 from the left. That means we're considering x a little bit to the left of the limit point 0, right? X is negative there. This is the square root of x squared. We talked about this last week some, not a lot, but a little bit. This is the absolute value of x, right? So the absolute value of x is equal to minus x if x is negative. For example, what's the absolute value of minus 5? Absolute value of minus 5 is minus 5, right? So we have to put a minus there because it's the absolute value. So once you put that minus there, they cancel. That leaves you minus 1. The limit there is minus 1, right? Once more, if you're uncertain here, you could have done something like plug in minus 0.1 into this expression. And if you had plugged minus 0.1 into this expression, you would have gotten minus 0.1 upstairs divided by the square root of minus 0.1 squared, which would have given you 0.1. So you have minus 0.1 divided by 0.1, which would have given you minus 1. You could check, like if you're in doubt, perhaps a numerical method is a good backup, right? But it's only a good backup in as much as it's one of the problems where I say you don't have to show your work, right? Now, if it's a problem where I say you have to show your work, you could document it by actually writing down the numerics, and that would get you some partial credit, right? This one here, limit as x goes to infinity of inverse tangent, I personally would solve that graphically because the graph of inverse tangent looks like that, and so the limit's pi over 2. However, another way you could have figured this out, take your calculator, take the inverse tangent function, and send like 1,000,000 to it, see what happens, right? Remember, we work in radians, so you need to be in radian mode if you're going to do such a thing, right? Otherwise, you're going to get 90 degrees, which will give you partial credit on this problem, but that nevertheless, we talk about radian, the radian trigonometry functions in calculus. Here, this last one, log as x goes to 0 from the right of the log of x. Well, log of x looks like an exponential flipped over y equals x, so the graph is like this. You know, it's got this x-intercept of 1. Log of 1 is 0 for any log base. And so as you go to 0 from the right, you're going to minus infinity. Again, if you were unsure about the graph, if you just didn't know this, if you're in doubt, get your calculator out. Take the log of like 0.001, see what happens. You should see that you get more and more negative large numbers as you get closer and closer to 0. That's problem 1. Problem 2, so some of you were like thinking that this problem was somehow like, you know, exactly the same as like my problem 78 comment that we talked about before the quiz. That wasn't the case. This one is simpler than that, because this one here, we just have the limit of the above and the below functions both going to 4. That means that they squeeze the limit into existence of the middle function f of x. Therefore, the limit as x goes to 1 of f of x is equal to 4. So some of you like had like half of this, but you never actually had the conclusion limit of f of x equals to 4. All right. Notice that I always write limit of f of x equals to 4. I don't like just write limit equals to 4. Yeah? You never seen me write limit equals to 4. You shouldn't write that either, unless you're going to define it systematically and use it, at which point I will then have to amend my instructions to disallow it on the next assignment. But there seem to be no math majors of that ilk in this class. I'm not sure, maybe you're just withholding your sarcastic math comments. I don't know. But this one here, problem 3. So here I asked you to show your work, right? Oh, that reminds me. I found my lasers. All right, so here, not like a bunch of you have factored. So this is something we're going to have to get out of our system, right? This can be fixed, though. You guys can unlearn this. So some of you have done this. All right. If you were in Dr. Sprano's class and you did such a thing, I'm pretty sure like next to that in like bold capital letters, you would have seen written bad algebra, right? Because this is bad algebra. Why is this bad algebra? What happens when we multiply this out? We get 2x minus 6, right? And this and that are not equal, right? So the judge of any alleged factoring is multiplication, right? Because factoring is unmultiplying. So this is in fact not equal to that. You can't do that. All right? If you were going to go down that path, you know, you'd need to do what? You can't just put a 3 there. You have to put a do what? You have to put a 3 over 2 because you pulled a 2 out, right? There has to be a 2 common to both terms in order to factor like that. Yeah? So factoring is using the distributive property, and the distributive property has to go across both terms. Like it's not enough to just have a number in just one of them. Like, let me write it out. So like 2x minus 3, we'd write 2x minus 2 times 3 halves. That's something you can do, right? Any number divided by 2 multiplied by 2 is the same number. This is something you can do. Once you have that, you've got a 2 common both places, so you can factor 2 out. But without the 2 on both places, we can't use the distributive property to factor out the 2. All right? So this is algebra, right? If you did this, there's a significant chink in your algebra armor. You need to fill that in so that I can't shoot an arrow through it again, you know? I view the professor-student relationship as a somewhat adversarial relationship. I'm not always trying to kill you. So just, you know, as a means of it out. Okay, that's not actually true. I'm a benevolent dictator, but all right, so I do want you guys to learn. And that's why we're having quizzes in here. You know, my life would be easier if I didn't grade 11 quizzes in here. But I'm making a point to take time in my week to grade a quiz of yours so you have feedback every week about how you're doing in the last week's material. This is not to decide how smart you are or to assign your grade, really. I do have to give you points, because if I don't give you points, you guys will check out. It's just a fact of students' existence. If you don't assign points to something, students read that as professor does not care, right? Is it not the case in your other courses? Do you do the stuff that people don't give you points for? You don't. I wouldn't. So, I mean, it's the same for faculty. Like, this training, is it required or not required? Not required. Oh, okay, thank you. Music to my ears. Anyway, but we're actually doing something profitable here, so let's continue. So this one is a difference of squares. See, that's 2x squared minus 3 squared. So I can factor that as 2x minus 3 times 2x plus 3. Okay? Once I do that, we've got a common 2x minus 3 above and below. Now, I can't just plug in the limit point from the outset, right? Because when you do, you get 0 over 0. Some of you have written 0 over 0 equals the limit. This is not good. I said, don't do that. All right. Also, some of you have not written limit where it belongs, and others of you have got like arrows or something between an arrows and an equality. I don't know. There's a great diversity in not showing work in here. As you know, diversity is our strength, so the class is much stronger now. But so notice I'm very boring. I use my original problem statement as a jumping off point. I say this is equal to that. Then I do algebra here, and I keep writing the limit until I take the limit. All right? So this is my typical notation. Is this the only way? It is not. Let me show you an alternative way. If writing limit is such a problem, an imposition to you, let me show you another way. There is another way you could denote your work for limits. But if you do this, you have to do everything I'm saying, not half of what I'm saying. All right? And I do this sometimes. It is a legit other notation. It's fine. It's just that you should understand that the limit notation does part of this for you. So let me write the same solution with a different notation just to kind of talk about this. Okay, so I can say, suppose x is not equal to what? X is not equal to 3 over 2. All right? Then 2x minus 3 over 4x squared minus 9 is equal to 2x minus 3 over 2x minus 3 times 2x plus 3, right? These cancel. So, which is equal to 1 over 2x plus 3, all right? And this, so thus, minus 3 over 4x squared. Well, all right, you guys want to be lazy, right? So this goes to 1 over 2 times 3 halves plus 3 equals to 1/6 as x goes to 3 halves. So the key is I'm declaring to the reader that we're considering x not equal to 3 halves. See, the limit notation does that for you. When I write that notation, limit x goes to 3 over 2, and I put parentheses, it's declaring the algebra I'm doing within the parentheses is subject to the terms and conditions, x not equal to 3 over 2, which makes those algebra steps I did legitimate. Do you guys see the issue? Now, if you just do algebra without the limit notation, then you're, being sloppy. And if you just have the bigger problem, of course, besides just that, that's like one issue. The other issue is you don't have connecting equalities between your expressions. So like, we want to have a flow of steps, a flow of logic. And so if one thing is equal to the previous thing, you need to write equals. If it's not equals, if it's applying a theorem and a thought, you don't write equals. You write a sentence or you write an implication, right? Equals and arrow mean different things. So we want to write the best thing to communicate the logic of what we're doing. All right? That's the general principle of things. But we're all learning this, right? If I'm teaching pre-calculus, am I that picky about showing work? I'm less picky because I have other battles to fight there, right? But here, we're trying to be more careful. I'm trying to prepare you for what will be demanded of you in Calculus 2, among other things, all right? Anyway, that limit worked out to 1/6. Now this one, I'm sympathetic if you didn't know how to do this. We haven't spent a lot of time talking about logarithms, but some of you figured this out, so great. Okay, so here the issue is that's infinity minus infinity, because if you plug in a positive number a little bit bigger than 2, you get log of something that's close to 0, but positive. So, I mean, I wrote infinity minus infinity. Technically, this is actually what? I mean, to be fussy, it's actually minus infinity plus infinity, right? If you were to actually fuss with the numbers. But we just write infinity minus infinity for that as well. If you wrote minus infinity plus infinity, that'd be fine. Actually, you didn't have to write any of that. That is a comment there to help you understand why we're doing algebra, all right? Because this is an indeterminate form. All right, so where's my laser? My laser. I just had my laser. I've already lost it. So sad. Oh, here they are. All right, so properties of logarithms. The log of a difference is the log of the quotient, right? The difference of logs, rather, is the log of the quotient. And then I can factor this here, x squared minus 4. Difference of squares, as usual, x minus 2, x plus 2. The x minus 2's cancel. I'm just left with the natural log of x plus 2. But that, you can just plug 2 into, and you get log of 4 as the answer. So there's that. This one, you should have got right, because we had a few of these. We've spent more class time on these, for sure. I don't think I did that one above in class yet, right? That would be a combination of things we've talked about. And so if you didn't get it, I'm totally sympathetic to that. I do put 20 bonus points on the quiz. So like if you got everything else right, you'd still have 100, 10 out of 10, right? Anyway, so here the trick, the technique, if you will, is to multiply by sort of the conjugated version of it. You take the radical plus 1 instead of the radical minus 1, like that. And then we multiply it out, and take the difference of squares. Well, just simplify this, right? This simplifies to 1 plus h minus 1. The 1's cancel. Then the h's reduce. Some of you are canceling the h's to leave you a 0 in the numerator. That's not right. When you cancel the h's, it leaves you a 1 upstairs, right? Like 1 minus... I got to get some new lasers. Come on. Oh man, this one's dying the same death my red one died last semester. So sad. Anyway, so the 1's cancel, then you have h over h. H over h is not 0. H over h is 1. And so that puts that 1 there, and then you plug in 0 and you get 1/2. So there's that. All right, let's see here. This one, so you plug in 2 and you get 0 over 0, like, uh-oh, got to do something, right? But if you plugged in 2 and you got 0, that means that x plus 2 will factor. Will factor, excuse me, x plus 2. If x equals 2 makes it 0, that means x minus 2 is a factor, right? So that means I can definitely factor out an x minus 2 in the denominator. All right, now I was like, so once I do that, I know that I need an x squared here, because I have to have x times whatever is here, gives me back that x cubed, right? And if I put a minus 2 there, that forces me to put a 2 here, because I know that this has to multiply back out to give that, right? But I wasn't sure when I first did this if there shouldn't be a middle term, because I didn't just do the simple thing, which is multiply it out and see if it works, right? But it does. See, because this gives you x, come on, x cubed plus 2x minus 2x squared minus 4, which is exactly what we have over here. So you multiply that out, it gets that. So that's how that factors. Yeah.
I put limit. How is that incorrect?
You can talk about it after class. I can't talk about corrections in here right now. Yeah. But I do welcome talking about, if I miss things. So like, it's totally acceptable to talk to me about after class about, corrections to my grading. I am human, I do make mistakes. I welcome those questions. So, just after class. So, now here, this is a way you could have factored the cubic, right? Suppose this problem isn't as nice as it is, you actually need a middle term. Long division will help you factor. You can divide x minus 2 into this cubic. It will tell you what the cofactor to x minus 2 has to be in order to factor x cubed minus 2x squared plus 2x minus 4. It just so happens that it's just x squared plus 2. Anyway, so once you have that, you cancel the x minus 2, right? And then you plug in 2, you get 1/6. And then finally, last but not least, the proofy part. So here, hey, signs of life, lots of signs of life with you guys. Almost everybody put let epsilon be greater than 0. Some of you just put epsilon greater than 0. You're missing a let. Let epsilon be greater than 0, period. Just start like that. You got 20% of the credit right there. So then we're going to choose delta equal to epsilon over 4. Sorry, my pen's jumped or something. If I then let 0 be less than x minus b minus 3 less than delta. Now some of you have chose a condition here which is not that. Like you have to, this is the next thing, is to suppose that you're within basically within delta units of the limit point, which is what this inequality says. The distance from x to 3 is less than delta. That's what that's saying. Now I consider f of x minus L as absolute value, which in this case is 4x minus 10 minus 2. That simplifies to this. You factor the 4 out, you factor the 4 out, and then that's less than 4 delta by assumption here. We read top down, which gives us epsilon. Therefore, the limit is 4x, s goes to 3 of 4x minus 10 equals to 2 by definition of the limit. And again, my apologies for the lack of creativity in the prose here. It is the same basic paragraph every time for the linear problem. If you don't understand what's happening here, and I almost never say this in calculus, but there is a subset of you who are just not mentally where you need to be yet, mathematically speaking, to understand this. It's just a fact. It just happens. There's a subset of you guys who are just not ready for it, and that's okay. For you, memorize this if you want the points. Right? That's like the only time you're ever going to hear me say memorize something in here. It's it. So pay close attention. But you know, you could memorize this template as a means to do this problem. All right. So that's that. Any questions about where we are, where we're going? Again, if you have questions about grading, I'll talk to you after class. Yeah? All right, so today we're talking about continuity of functions, and I'm gonna use my notes here for a second because I just don't want to write out some of this stuff because it's kind of, you know, I got some nice pictures in the notes I'd like to point at with my newly found laser. So, and I don't actually expect you to know the definition here. I want you to read it and maybe appreciate what it's saying. But what I actually want you to know, to have, let's say, memorized. Memorized might be the wrong word here, but you certainly should be well, no, memorized is probably the right word. You need to know it and be able to apply it. So I guess that means I'm asking you to memorize it, doesn't it? Doesn't it? Let me see if I can turn off these lights so it's a little bit less washed out. So today we're talking about continuity of functions. So to start with, I need to just give you, like, what's the definition of continuity of functions, all right? So, so here's the definition. Let f be a function, and then you got a point in the domain of f. Then f is continuous at that point in its domain. If and only if for each epsilon greater than 0, there exists delta greater than 0 for which the absolute value of x minus a less than delta implies the absolute value of f of x minus a is less than epsilon. Okay. And then if f is continuous for each x in U, then f is continuous on U. And then f is continuous on its domain means f is continuous overall. So before I go on, can you guys spot the difference between what's written in this green box and the definition of the limit we were just working with in the quiz? What's the distinction? It actually looks a lot the same if you look at it, right? There's a delta, there's an epsilon, but there's one important thing missing. See this here? What's missing? In the statement of the limit, we do what? 0 less than absolute value of x minus a. So what is this saying? Does this disallow x equals to a? It does not, see? So the continuity considers a. So it's not quite the same. It's very close to the limit, except now we do consider at the limit point. All right, we do consider the limit point when we're considering continuity. I cannot even entertain the question, is a function continuous at a point outside its domain? That question doesn't even make sense to us. We only consider continuity of functions at points within their domain. All right? And so if you want some pictures to basically communicate what that definition's doing, basically it's saying, so if you're at a point in the in the interior of the domain, for every like epsilon plus or minus epsilon band, there's a plus or minus delta band so that the entirety of the graph, even including x equals to a, is within the zoom window. Now for the limit itself, we actually have a dotted line right down the center because you don't actually consider x equals to a. So the limit could exist at a hole in the graph, but for a hole in the graph, we can't even discuss continuity at a hole in the graph because a hole in the graph is by definition outside the domain of the function. But this definition also concerns boundary points. So like if your domain, if the graph of the function's like this, so you've got, like a, this boundary point, then the continuity there would be judged by a right limit. Right? It's kind of like a right limit for that kind of thing. And again, the idea is that if you zoom in, the graph of the function doesn't jump outside the zoom box, right? And again, for a right boundary point, you can zoom in, your function doesn't jump outside the zoom in box, all right? And just to get to the point here, this is what you actually need to know, and we're going to work problems with here in just a moment. And I'm going to put these notes away just a second. Once I want to look at the notes to write out things that are boring to write. Okay, then we'll work problems today. So this is basically it. Characterizing continuity at a point. All right. So if you have a point, basically f is continuous at a in the domain provided three different cases. If a is in the interior of the domain, away from the edges of the domain, it must be the case that the double-sided limit of the function exists at that point, and it's equal to the value of the function if you just plug in the point. In other words, the limit as x goes to a of f of x is equal to f of a. Oftentimes, this is what we mean by continuity at a point. Now, if it's a left boundary point, then we must judge by the limit as x goes to a from the right of f of x equals to f of a. If it's a right boundary point, then we have to take the left limit as x goes to a from the left of f of x equals to f of a. Right. So now here's a picture of discontinuity. See here, if this is a jump, right? Notice that that dot's filled in so we can at least entertain the question of continuity because there is the domain includes that point. But if you pick an epsilon band over there, there's no possible way you can pick a delta band such that you don't include points in the graph which are more than epsilon units away from the value of the function at a. So this is a place where the function's discontinuity. Discontinuity at x equal to a could look like that. Let's see here. Now, you're probably taught in pre-calculus that a continuous function is one whose graph is drawn without lifting your pen. I mentioned this the other day. We don't quite agree with that in here, to be truthful. There's a subtle point here, which is that this function, the reciprocal function, y equals 1 over x, is a continuous function. F of x equals to 1 over x. What's the domain? The domain is x not equal to 0, right? So the place where this function is discontinuous, 0, is outside the domain of the function. So in terms of our definition of continuous, we can't even entertain the question of is this function discontinuous at 0. So in short, the reciprocal function is continuous on its domain. And by our definition, that makes it a continuous function. Right? Yeah, of course, can you draw this graph without lifting your laser? No, right? So that pre-calculus intuitive definition of continuity of a graph, it needs to be modified a little bit. See, that's only good if the domain is what's called an interval. What's an interval? What, like this?
In between these two values.
In between these two values, or how about this? I don't. My arm's not long enough for it, but you know, it keeps going and going and going and going. If I was like that Incredibles, you know, like the stretchy person, is it the mom? Elastigirl. Yeah, I don't want to be a girl. Actually, I'm see here. I know. Anyways, yeah. Is there an Elastiman? Oh man. Any other university I could gender swap it, it'd be fine. But anyway, so my point is you have raised to infinity or to minus infinity, right? Those are also intervals. There's 10 kinds of intervals. Open sets, closed sets, half open, half closed, one way or the other, and then the rays that either go to infinity or minus infinity, either including or excluding the finite point. 10 types of intervals, and also the whole real numbers. The intervals of real numbers are the connected sets of real numbers. So connected sets of real numbers are the real numbers, the subsets of real numbers that you can draw on the number line without lifting your marker. right? Now, the rays, you got to go on and on forever, so you're going to be here while drawing it, right? But nevertheless, these are connected subsets. So with respect to a connected domain, the pre-calculus definition makes sense. If your function has a connected domain and you can draw the graph of the domain without lifting your pen, it's a continuous function. On the other hand, if you've got a connected domain and you cannot draw the graph without lifting your marker, it's a discontinuous function. There's got to be a jump discontinuity in there somewhere. All right. So people who are smarter than me find a way to hide this. I just don't hide things that are confusing. I try to bring light to them. All right, so then we'll come back to this example in a minute. I just want to go ahead and jump past this and just point out this is a list of all the functions which are continuous on their domains. Polynomial functions, rational functions, algebraic functions, trigonometric and reciprocal functions, exponential functions, I killed it. Hyperbolic trigonometric functions and their reciprocal functions, as well as their inverse functions. These guys are all continuous on their domain. All right, so the places where there's discontinuity, it's exactly where the formula breaks down. So that's just a snapshot of what we have to expect. But anyway, I'm going to put this away and let's work some things out piece by piece. All right. So let me get the lights back on in here. So when's our test? Let's see, did I tell you when the test is? Or do I just I feel like a test this Thursday. Is that how I do things in here? I do not, right? Everything's on your course planner. You can look there, February 8th. Also known as, what is that? That is it's the 8th of February. Thank you for that. That was helpful, but true. I mean, that's a tautology right there. The 8th of February is the 8th of February. Who can disagree? Yeah, it's also known as next Thursday. Although there's a disagreement about that. Some of you are like, next Thursday, that's tomorrow. Wait a minute, no. Tomorrow's tomorrow, right? But, but people who have the right understanding of this phrase, next Thursday, understand that that's 9 days from now. Is that right? 8 days? I don't know, depending how you count. I can't count, don't ask me. So, anyway, my point is that the test is upcoming. What does the test have on it? It has limits, right? It's mostly about limits. It's a little bit less about the pre-calculus review. I will test some aspects of the pre-calculus review. Some of your favorite, like the biggest hits might be on there, like the find C, A, and B, that problem. But it's more, the test is more focused on the limit, like the new material, all right? So, but is pre-calculus tested in this course? Yes, always. There's always pre-calculus in everything we're doing. Okay, so let's talk about a theorem here. If f and g are continuous at x equals to a, then 1, f plus g, 2, a constant times f, 3, a product of f and g, and 4, in as much as it makes sense, f over g, and 5, in as much as it makes sense, f, well, this I got it. I'll make that a separate theorem, f over g. These guys are all continuous at x equals to a. So now to keep the discussion simple, I'll consider the case of an interior point. Let's suppose that a is interior to both the domains, just to keep things simple. So here's the proof, and a is an element of the interior of the domain of f and also the interior of the domain of G. That's just a fancy way of saying we can take, it's meaningful to take the double-sided limit of both of these functions, all right? So if we assume continuity at A, that means that we're given that the limit as x goes to A of f of x is equal to f of A, and the limit as x goes to A of g of x is equal to g of A. All right? Now, so how do we prove 1, 2, 3, and 4? It's very silly, almost. Simple. So to prove 1, check this out. The limit as x goes to A of f plus g of x, what's that defined to be? How do you define f plus g of x? Do you guys remember how we added functions? We added them pointwise, right? So the rule for the f plus g function is that you have f of x plus g of x. That's the formula for f plus g. But then we can use yield limit laws, right? Hey, we proved this one, didn't we? I didn't prove too much in here so far, but this one we actually did. Why can I make that step? How do I know that the limit of f and the limit of g exist? Well, you're like, well, you just wrote it the line above, so maybe that's a clue, right? So these exist, I can apply the additive law for limits, but more than that, this is given to be what? This is f of a, this is g of a, so we've got f of a plus g of a, which is, by the way, f plus g of a. So therefore, the sum of the two functions, f plus g, that new function, is itself continuous at a, because the limit as x goes to a of f plus g is actually equal to the value of f plus g at a. So the sum, let me put it in words, the sum of two continuous functions at a point is continuous at a point, right? And you can extend this. If they're both continuous on some set of values, then the sum of the functions is also continuous on that set of values, right? Like if their domain was all real numbers, right? If you have two continuous functions on the whole set of the real numbers, then the sum of those two functions is also continuous on the whole real number set. If you don't understand what I'm saying, I'm drawing a distinction between continuity at a point and continuity on a set. To be continuous on a set means that you have continuity at each point in the set. All right, so it's a slightly different idea. Okay, so then 2, you guys tell me how would I do 2? It's kind of silly, isn't it? CF, how do you define the function CF? It's defined to be c times f of x, right? That's the formula for CF. And then by limit law, that is c times the limit as x goes to a of f of x, which is equal to c times f of a, which, by the way, is the CF function at a, right? So the c times f function is continuous at a. 3, limit as x goes to a of f times g of x. How do we find that? Well, the limit of the product function is defined by the product of the values, right? And then we can use the product rule, which I have warned you guys is a little bit technical to prove. Still haven't made my video about that. Sorry about that. Maybe I'll get to it eventually. Again, that wouldn't be required viewing if I did. So this is the limit of a product is the product of the limits provided the subsequent limits exist. And so that gives us f of a times g of a, which is fg of a. So the product of continuous functions is continuous. So the sum, the scalar multiple, the product of continuous functions is continuous. For 4, what do I need for 4? There's always fine print with a quotient. What's the fine print? G can't equal, did you say g of a or did you say g? I couldn't. You just said G. Okay, so that's almost right, but we need what? It would be okay for G to equal 0 some other places, but at A, that's the trouble, right? So here we need G of A not equal to 0 in our current, conversation. So in that case, you can basically just, same as we just did for the others, right? F over G of X is equal to the limit as X goes to A of F of X over G of X, right? Which is equal to, provided these limits exist, but they do because we're assuming that the functions are continuous at the point A. So that's F of A over G of A, which, by the way, is how we defined the quotient of the two functions. The F divided by G function is defined at each point to be the value of the function is given to be the ratio of the numerator function divided by the denominator function at the point. So, don't be afraid if I ask you on the test, prove that the sum of two continuous functions at A is continuous at A. That's actually not a hard problem. You just have to simply apply essentially our definition of continuity. Okay, fine, that's not exactly true. My definition was that green box. I'm really applying the theorem which characterized continuity in terms of limits, right? But for all intents and purposes, that's essentially our definition. It's equivalent to our definition anyway. So the characterization is that a function is continuous at a point if the limit of the function is given by just evaluating the function at the point, right? So with that in mind, and the limit laws in mind, proving this theorem is actually not that bad, right? Surely this is easier than the last problem on the quiz with all those pesky epsilons and deltas and stuff, right? All right. There's one other one that's a little bit trickier. Another theorem that I should mention, which is that if, let's say F is continuous at A and G is continuous at F of A, then G composed with F is continuous at X equals to A. So this is the composite. All right, so here's how that goes. If we're calculating the limit as X goes to A of G composed with F of X, how's that go? Right, the G of F of X. And well, so this isn't, I really shouldn't put proof here because what I'm doing right now is not really a proof. I'm just trying to explain to you how it works. To do a proof, I'm going to have to drop back to the epsilons and deltas, I think. And maybe we'll do that. I just don't want to do it right now. I don't think I have quite enough time to do that and to do the things that I'm interested in here. So the concept here basically is that, oh, you know what? I just thought of it. I'm sorry, guys. I just thought of how I can maybe make this more convincing to you. So let's just think of it in terms of a substitution. All right, so like let y equals to f of x, right? If x goes to a, then y goes to what? At y goes to f of f. Y equals f of x goes to what? If x is going to a, y equals f of x is going to f of a, right? That's continuity of f. All right? So if I make this substitution, if I change the limit to y, I should change from the limit as y goes to f of a of g of y, right? But then what? What's the limit as y goes to f of a of g of y? Well, we assume that g is continuous at f of a, right? So that's equal to, by the assumed continuity of g, g of f of a, which, by the way, is the composite of g with f at a. So that goes to show you that the composite of two continuous functions is continuous, right? Assuming that they can be composed, right? I do have to have the domain of the functions being composed, and they have to be composable functions. All right, so those are basically so what I'm trying to tell you here is simply this, is that all of the limit laws that we studied before, they have straightforward corollaries to the theory of continuous functions. Like every limit law has a corresponding statement about continuous functions. The additive rule for limits gives us that the sum of continuous functions is continuous. The multiplicative rule for limit gives us that the product of continuous functions is continuous. The ratio rule for limits gives us that the ratio of continuous functions is continuous. The composite rule for limits, or if you like, the substitution rule for limits, actually gives us that the composite of continuous functions is continuous. You put all this together, what that means is that if you're faced with some kind of horrible mess like this, I don't think I did an example yet, did I? Nah, let's call this example 1. So suppose you got like the limit as x goes to pi of, I don't know, the hyperbolic tangent of, the sine of x squared plus 7, plus 2. Well, I mean, that's kind of a mess, but let's think about what we're looking at, right? You're looking at a composition of different functions, right? Like what's going on here? First of all, I got x squared plus 7. That's a polynomial. A polynomial is formed by what? Just product of x. We already know that x is continuous, right? We do? Remember, we proved the limit as x goes to a of x is a. That means that the function x is continuous. So this x squared plus 7 is continuous. Sine is continuous everywhere, all right? I guess I haven't proved that yet. Maybe I'll do it later this week, but anyway, so the inside function is continuous. Sine is continuous, so that composition is continuous. Adding 7, right? Is the 7 function continuous? Is the constant function continuous? Yes. So then we've got the sum of two continuous functions is continuous. So the input to the hyperbolic tangent is a continuous function. The hyperbolic tangent itself is a continuous function because it is formed by the ratio of exponential functions. Exponential functions are everywhere continuous. So all the way down, this is the composite of continuous functions. Therefore, it's continuous. Therefore, I can just plug that number in. And so that's the ultimate, story here, is that this is what justifies what I've been telling you already, which is that the first thing you try to do is just plug the number in. And, that is what it is. Now, where does this break down? This breaks down if we have an indeterminate type, right? If when you plug in the limit point, your formula doesn't agree. with the laws of arithmetic. You've got division by 0, the square root of a negative number, the log of a negative number. These things we can't do, all right? Okay, so let me look at the other kind of example here that is interesting. Let me write up the example. Let you guys think about it for a second here. So see if you can figure this out. Choose C such that f of x equals case-wise defined. All right, so we're going to do 2x plus c, and then x squared plus c. All right, and this will be for x greater than 3, and this will be for x less than or equal to 3. So my question is this: can you choose c so that this function is continuous on the real line? So the domain of the function is everything. We'd like for this to be a continuous function. To be a continuous function means it must be continuous at each point in its domain. So since the domain here is all real numbers, oh man, I'm sorry, I forgot to move the camera down. Oh man, this is a bad one. Sorry if you're not here. My apologies. Oopsie. I must make a comment. Look ahead to minute 56. Sorry, guys. Well, you guys are here. What do you care, right? Yeah. So what do you guys think? Can we figure out a value c such that this function is continuous? First of all, let me take care of all the easy part. Right? There's two very easy cases. Two easy cases. First of all, if a is less than 3, the limit as x goes to a of f of x is equal to what? Which case are we in? If a is less than 3, we're in the second case. So the answer here is x squared plus c, right? And so that would just give us a squared plus c, which would be, by the way, f of a. So hooray, this function is like pretty much automatically continuous at those points. How about a greater than 3? Is the function continuous over there? Well, it's kind of, I mean, I don't know. I mean, sometimes I don't even write this out. I just like, the function is, I will just have a sentence. This function is clearly continuous at every point except for 3. But I'm writing it out because I think it's healthy for us to do this. So this is 2a plus c, which is equal to f of a. Great. It remains to establish continuity at, x equals to 3. And what's the logic here? For the limit at x goes to 3 to exist, we must have what? We must have the two-sided limit exists, right? So we need that the two-sided limit exists. So to get this, we need two things, right? We need the limit as x goes to 3 of f of x, exists and is equal to f of 3, right? What is f of 3 equal to? The question's not ambiguous. What's f of 3 equal to? There's only 3 is only in one of these cases. Right. So 3 squared plus, so I hear 9 plus c. Yeah. So 3 squared plus c. So that's f of 3. Now for this to exist, what do we need? We need both x goes to 3 from the right and x goes to 3 from the left to give